Hello. Today we're going to look at difference of cubes, which is necessary for understanding why a cube root isn't necessarily going to have a single value, why each number that is not zero actually has three cube roots. Two of them are often complex, at least. For example, 1 is going to have 1 as a cube root, but in fact there are two complex conjugate cube roots. So before we start, let's look at this question right here. Does a squared equal b squared imply that a is equal to b? Think about it for a second and see if you can determine whether or not this is true. Find a counterexample or maybe prove that it must be true. So, it turns out this is actually false, and we can check right away by finding a single counter example. So, let's say we have 1 squared equals negative 1 squared. Obviously, if this were true, we could say 1 is equal to negative 1, but that doesn't make any sense at all. So, we already know that this right here is not true. Not always true at the very least. In some cases, it will be true, but how come this happens sometimes? Right here, a common mistake would be to say a squared is equal to b squared. And so I can take the square root of both sides, and of course the square and square root cancel out, or at least that's the idea. And if they were to cancel out, what we'd end up with is a equals b. But the problem here is that we can't just take the square root of both sides. This is actually a difference of squares. So, if we have a squared equals b squared, we can subtract b squared from both sides and say that a squared minus b squared is equal to 0, right? And if a squared minus b squared is equal to 0, we have a difference of squares, as I mentioned earlier. So, this is actually a minus b times a plus b. And by what's known as the null factor theorem, we say that either a minus b is equal to 0 or a plus b is equal to 0. And that's pretty obvious, because if they weren't 0, the product wouldn't be 0 either. And this means that either a equals b or a is equal to negative b, which is what we see right here. 1 is equal to negative 1. And that's all that it implies. It doesn't always imply that a equals b. It actually implies that a is equal to plus minus b. Now, you might think that this holds true for odd powers. For example, a to the n equals b to the n does imply that a equals b if n is an odd integer. But in fact, that isn't true either. And that's because, in fact, there's a nice formula for factoring a difference of cubes, and a difference of fourth powers, a difference of fifth powers. And in general, we can say that we could factor a to the power of n minus b to the power of n. What's the formula? We'll find out. I'll show you later. But let's look at this specific case. It's really hard to figure out a and b that aren't equal, that make this true, because for the most part we've been learning about real numbers. But if we look at complex numbers, in fact, this does happen sometimes. So, what if a is equal to 1 and b is equal to, and I hope I have this right, minus 1/2 plus square root 3 over 2i. You can test these numbers out for yourself. You cube each of them, and the fact is, you get back to 1. And these obviously aren't equal, are they? How can we find this? Once again, difference of cubes. So, let's look over here at a cubed equals b cubed. Once again, we're going to have 0 on one side, and then on the other side, we're going to have a cubed minus b cubed. And I hope you see where that comes from. We're subtracting b cubed from both sides. Right here, 0 is equal to a cubed minus b cubed. And I'll just tell you how to factor it without showing you why it's true. You can verify by expanding. 0 is actually equal to a minus b times a squared plus ab plus b squared. And this is where this comes from. You see, by the no factor theorem again, either a is equal to b, or we're looking at solutions for this equation here, a squared plus ab plus b squared equals 0. This is a quadratic equation, and in fact, for the most part, you're going to have two distinct roots. As you might notice, a minus b always seems to be a factor for a to the n minus b to the n. How do we know that's true in general? And the answer is the factor theorem. So remember, the factor theorem says that for a polynomial f of x, if f evaluated at a is equal to 0, that is to say a is a root of f, x minus a is going to be a factor for sure. And this is actually where this comes from. We're going to use a little trick here, a little bit of creativity. So we're going to say that f is a function of a that's equal to a to the n minus b to the n. And what is the purpose of this? We're going to say that a is our independent variable and b is like a constant. We can treat it as if it's a constant. And what we notice is that if we plug in a equals b, we'll have f of b is equal to b to the n minus b to the n, which is equal to 0. In other words, a minus b is certainly a factor. That's where this comes from. And it turns out that when you divide by a minus b, divide a to the n minus b to the n by a minus b, we get this factored form right here. And if you don't believe me, we're just going to quickly do an example with the difference of cubes from above. And we're going to do it using synthetic division because it's faster and it's a little less conventional. So, right here, remember, synthetic division, you just need to write in the coefficients. So, because a is our independent variable, it's our input for the function, it's our argument, we have a cubed, a squared, a, and then 1. The coefficient of the a cubed term is 1, the coefficient of the a squared term, there's no a squared, so it's 0. Similarly, there's no a, so that's 0. And here for our constant term, because we said it's a function of a, we can treat this as if it's a constant. So we have minus b cubed. And if we're dividing by a minus b, we need to negate this term here, the constant term, and just write that version, b. To perform this division, we need to bring the 1 down, multiply, and put that new number there. And once again, we add up the column, we have b, then we multiply to get b squared and place it in the next column. We add it, that happens to be b squared, we multiply and bring it over here, b cubed, we add it together and we get 0. This checks out. Remainder is 0, this was indeed a factor. And it lines up with what we have here because we have a new polynomial where this is quadratic. So this is degree 2, degree 1, degree 0, and it's a function of a. So we have a squared plus ab, or ba, and finally plus b squared, our constant term. No remainder, and remember we divided by a minus b, so we have a minus b. And that's the result of our synthetic division. We can verify that, in fact, when we have a to the n minus b to the n, a minus b is a factor, and it happens to work out to be this nice series we have here. We can confirm this is true using proof by induction, but I'm not going to show that in this video. I just wanted you guys to have a bit of an intuition for why this works, for why it makes sense at all that this should be true.